In this video, I will be going through the binomial probability distribution, and this particular topic is related to the discrete random variable, meaning you need to understand random variable in order to understand this topic. Right, let's go through the syllabus. Notice that this is actually meant for math analysis and approaches standard level, but of course this material may also be relevant to other programs such as A level. Alright, so basically the expectation after learning or going through these videos is that you're able to understand when do we apply binomial distribution, or when binomial distribution is an appropriate model. And also the requirement is for you to be able to use the available technology, in this case the Texas Instrument Calculator, to find binomial probabilities. Next is the mean and variance. We'll go through these. Mean and variance of the binomial distribution, and we are not going to prove how to find the mean and variance formula. Rightio. Okay, now let's go through the condition of binomial experiments. Number one, the experiment is repeated for a fixed number of trials where each trial is independent of other trials. Number two, there are only two possible outcomes of interest for each trial, and they can be classified as a success or as a failure. Number three, the probability of a success, usually labeled P of S, is the same for each trial. And lastly, the random variable X count the number of successful trials, right? And here are some common notation. N is the number of times a trial is repeated. Lowercase p is the probability of success in a single trial. Lowercase q, which is equal to 1 minus p, is the probability of failure in a single trial. Uppercase X, of course, is the random variable that represent a count of the number of successes in n trials. So it can be 0, 1, 2, 3, etc. until n. Okay, now let's take a look at some examples. Here the instruction says decide whether the given experiment is a binomial experiment. If it is, then specify the values of n, the number of trials, p, the probability of success, q, the probability of failure, and list the possible values of the random variable x. Okay, let's take a look at this case. Number one, a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable x represents the number of successful surgeries. Okay, so each surgery represents a trial, and there are 8 surgeries, right? Because it says a doctor performed the procedure on 8 patients, so there are 8 surgeries, and each one is of course independent of the others. Okay, and there are only 2 possible outcomes: a success or a failure. Successful surgery or fails surgery. Next, the probability of a success is 0.85, that's given there, 85%, for each surgery. And random variable x count the number of successful surgeries. Therefore, this is a binomial experiment, yeah, with n is equal to 8 surgeries or 8 number of trials. P is equal to 85% or 0.85, the probability of success. Q is equal to 1 minus P, yeah, 1 minus 0.85 is equal to 0.15. This is the probability of failure. And X, yeah, that represent the number of successful surgeries, can be 0 successful surgeries, okay, can be 0 successful surgeries, 1 successful surgeries, until 8 successful surgeries. So again, it is a binomial experiment. Okay, next one. A jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. Yeah, again, the random variable represents the number of red marbles. Okay, let's take a look. This is not a binomial experiment, and here are the reasons. The probability of selecting a red marble on the first trial is 5 over 20. Why red? Because that is the random variables. Okay, the random variable represent the number of red marbles being taken. Yeah, so we focus on selecting the red marbles, yeah, because of this. Yeah. So again, the probability of selecting red marbles on the first trial is 5 over 20. Because the marble is not replaced, okay, that's given here without replacement, then the probability of success, which is the probability of selecting red marbles, for subsequent trials is no longer 5 over 20. Yeah, so again, for the first trial, the probability of selecting red marbles is 5 over 20. If it is not returned, then the probability to get the red marbles the second time is no longer 5 over 20, but it is equal to 4 over 19 because it has been taken out by 1. Yes? So therefore, this also means the trials are not independent, and the probability of a success is not the same for each trial. Okay? Having said that, here is the binomial probability formula. Yeah. Although I mentioned at the beginning, the syllabus says the binomial probability will be calculated using calculated Texas instrument, but it is good to know the formula as well. Yeah, notice that this is just the same as the binomial theorem formula. Yeah, where you have n combination x multiplied by p, the probability of success to the power of x, which is the number of successes in n trials, multiplied by q, the probability of failure, yeah, to the power of n minus x. And this is just the formula for combination if you calculate it manually, but of course you don't need to. Yeah, you can use your TI calculator. Yeah. So again, this is how you find binomial probability using a formula. All right. Well, actually, this one here. Don't worry about this one. Yeah, this one here. All right. Okay. Now let's take a look at an example. A microfracture knee surgery has a 75% chance of success on patient with degenerative knees. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. Okay, now before we use the binomial probability formula, there's also another way to do it using tree diagram. Okay, so since there are 3 patients, therefore there are 3 surgeries. So this is the first surgeries. So you draw the 2 branches. S stands for success, F stands for failure, and then you draw another branch, yeah, like so. Again, S stands for success, F stands for failure, and you do the same thing for the third surgery. And then you label the respective probabilities. Yeah. Of course, the probability of success is 3 over 4. That's given there, 75%, which is equal to 3 over 4. Consequently, the probability of failure is 1 over 4. Yeah, there you go. Remember, the probabilities must be the same for binomial experiment. Yeah. Okay, now the question says find the probability of the surgery being successful on exactly 2 patients. So we need 2S, so it can be success, success, failure, which is this one here. So that's equal to 3 over 4 multiplied by 3 over 4 multiplied by 1 over 4. And that's equal to 9 over 64. Yeah. And also we can have success, failure, success. So that's 3 over 4 times 1 over 4 times 3 over 4. Okay, and that's equal to 9 over 64. And lastly, we can have failure, success, success. And that's just equal to 1 over 4 times 3 over 4 times 3 over 4. Okay, so we use the multiplication rule. Yeah, we draw a tree diagram and use the multiplication rule. Remember, this is independent, so we use multiplication rule. Having calculated these, yeah, then we add them, or we can do 3 times 9 over 64. So the probability of 2 successful surgeries is equal to or is approximately equal to 0.422. Yeah, remember, answer is usually in 3 significant figure. Okay, so this is method 1. Method 2, let's use the formula. Okay, again, the number of surgeries, which is n, yeah, number of trials is equal to 3. The probability of success, yeah, successful surgeries is equal to 3 over 4 or 75%. Therefore, the probability of failure is equal to 1 minus 3 over 4, which is equal to 1 over 4. Yeah, and what we want is 2 successes. Therefore, x is equal to 2. Okay, remember this formula? Yeah. So we are going to use this formula. Probability of 2 successful surgeries is equal to 3. That's n there, number of trial, number of surgeries. 3 combination 2 multiplied by 3 over 4 square times 1 over 4 to the power of 3 minus 2. Yeah. Remember the binomial theorem? The power of these or these 2 powers, yeah, must equal 3 or n, yes. So therefore we have 3 subtracted by 2, that's equal to 1. Okay, let's calculate this using TI. Let me clear this up first. Okay, we want to calculate the 3 combination 2. So let me move this a bit over there. So we want 3 combination 2. So we go to menu, calculate, sorry, and then menu, probability, and then we choose combination. Okay, and we have 3 combination 2's, so therefore we type in 3, comma 2. Okay, and then we can press enter. The answer is 3. Yeah, so there you go, you have 3 there. Then multiplied by 3 over 4 to the power of 2, that's equal to 9 over 16, and multiplied by 1 over 4 to the power of 1, that's just equal to 1 over 4. And the answer for the probability of 2 successful surgeries is approximately equal to 0.422. So there you go, using binomial probability formula. The third method is to find the probability of having 2 successful surgeries in 3 trials. Will be done using TI calculator. Yeah, so we go to menu, probability, followed by distribution, and then binomial PDF. PDF means probability density function. So you use binomial PDF when the question is asking for a specific X number of success. Yeah, so we click that. Number of trials given there, that's 3. Probability of success is 3 over 4. You can input either decimal or fractional values. Okay, doesn't matter. Here I put fractional value, and X, here we want 2 successful surgeries. Okay, so put 2, click OK. So there you go. Yeah, so the probability of having 2 successful surgeries in 3 trials is equal to 0.422. Yeah, because usually they ask for 3 significant figure. As you can see, using technology is much easier rather than using the tree diagram or using the formula. Yeah. Okay, next. In this example, a 6-sided die is rolled 3 times, and then you're asked to find the probability of rolling exactly 1/6. We could use tree diagram like before and apply the multiplication rule, or we could just use the calculator. Yeah. In this case, let's just use the calculator. Yeah. Right. Number of trials given 3 times. Okay, the probability of success in this case, the random variable is the probability of getting a 6. So, and that's just equal to 1 over 6. Yeah. And the number of successes that the question wants is 1, just 1/6. All right, let's input these to the calculator. Again, you go to menu, probability, distribution, and we use binomial PDF because this question is asking for a specific number of success, which is 1/6. Yeah, so we click that. Okay, and let's input number of trials. Number of trials is 3 because the die is rolled 3 times. Next, the probability of success is of course 1 over 6. Yeah, the probability of getting a 6, yeah, when the die is rolled 1 time is equal to 1 over 6. Sorry. Okay. And we want exactly 1/6. Right. So let's input 1. And then click OK. So there you go. That's the answer. Okay. 0.347. Yeah, very easy. Okay, moving on to the next one. Okay, in this example, a survey indicates that 41% of women in the US consider reading as their favorite leisure time activity. You randomly select 4 US women and ask them if reading is their favorite leisure time activity. Yeah? Find the probability that at least 2 of them respond yes. Okay, number of trials is of course 4. Yeah, because here you randomly select 4 US women, so n is equal to 4. The probability of success in this case, women consider reading as their favorite leisure time activity. Yeah, so this is considered a success. So the probability of success is 0.41. Yeah, this one here. And therefore, the probability of failure is equal to 1 minus 0.41. That gives you 0.59. Now, this is a bit different. In this example, you are asked to find the probability that at least 2 of them respond yes. So that means you have to find all of these probabilities. Yeah, we are not going to do this manually. We are going to use the calculator. Okay, let's clear this up. Go to calculate and then menu, probability, followed by distribution. Okay, now this time we cannot use binomial PDF because this example doesn't ask for a specific value of success. This question asks for 3, probability of 2, probability of 3, probability of 4. So we have to use binomial CDF. Yeah, cumulative density function. Okay, so number of trials, there are 4 women being asked. Okay, the probability of success is 0.41. Lower bound, well, the question says at least 2 of the women. So therefore lower bound is 2. And upper bound, of course, 4 because there are 4 women being asked. Yeah, upper bound is 4. So put 4 and then click OK. There you go. That's simple. Yeah. That's the answer. And again, usually the answer is given in 3 significant figure. Yeah. So probability of x is greater than or equal to 2 is approximately equal to 0.542. Very simple. Another example here. 60% of households in the US own a video game console. You randomly select 6 households and ask each if they own a video game console. Construct a probability distribution for the random variable x, then graph the distribution. Let's write all the given information. Here we have number of trials is equal to 6 because in the example it says you randomly select 6 households, so number of trials is equal to 6. The probability of success is equal to 0.6. That's given there. 60% of households in the US own a video game console. So this is our random variable. Household in the US own a video game console. Yeah, or the number of households in the US own a video game console. So the probability of success is equal to 0.6. Therefore, the probability of failure, Q, is equal to 0.4. Okay, so what we have to do, we find the probability for each value of x because we want to make the probability distribution or some people call it probability distribution table. Okay, let me show you how to find that. So x, yeah, can be equal to 0, 1, 2, 3, 4, 5, and 6. Remember, the random variable is the number of households in the US own a video game, and you're asking 6 households, so it can be none having a video game console, or just one having a video game console, until 6 having a video game console, because again you're asking 6 household, and you need to find these probabilities. Yeah. Okay, let's go back to the calculator. Clear this up. Go to calculate and then menu, and then go to probability followed by distribution. And in this case we are using binomial PDF because we want a specific success, value of success, yeah, when x is equal to 0, when x is equal to 1, until when x is equal to 6. So we click binomial PDF, sorry, this one here. Number of trials, okay, 6. You're asking 6 households, so 6. Probability of success is equal to 0.6, or 60%, yeah, which is equal to 0.6. And when x is equal to 0, when no household having a video game console, so this is 0.6, and this one is 0. Click OK. There you go. That's equal to 0.004. That one there. Okay. And then next, when x is equal to 1, or when only one household owns a video game. So let's find that probability. Okay. So we go to menu, then probability distribution, and then binomial PDF. Number of trial is 6. Probability of success in this case is 0.6. Yeah, that's given. And we want x is equal to 1. That's what we want. Okay, so 1. Click OK. There you go, 0.037. Yeah, and you can do the same thing for x is equal to 2. So when only 2 households owns a video game console, or when x is equal to 3, or 4, 5, and 6. And then you can have a complete probability distribution. Yeah. Okay, next what we have to do is make the graph. Yeah, we don't have to do this by hand. This is only an example. Okay, so we know this probability distribution. Then we can create the histogram. Yeah, this is not in the syllabus. Yeah, I include this example just to give you an idea that you can use to develop your IA. Yeah. So we can have the number of households from 0 until 6 in the x-axis, yeah, and in the y-axis are the probabilities, and then you can draw the histogram and see the distribution, yeah, which is left skewed or negatively skewed, yeah. Right, next we're gonna go through the mean, variance, and standard deviation of binomial distribution. Suppose x, uppercase X, is a binomial random variable with parameters n and p. So x, a random variable x, has a binomial distribution with parameters n and p. So when you see this notation, this is what it means. Yeah. The mean of random variable x is mu, which is equal to n multiplied by p. N is the number of trials, yeah, n number of trials, and p is the probability of success. Remember earlier in the syllabus that says formal proof of mean and variance, including standard deviation, it's not required. So I'm not going to go through the formal proving, yeah. And also the standard deviation of random variable x is equal to sigma, yeah, which is equal to square root of np, okay, that's np, the mean, multiplied by 1 minus p. Notice that 1 minus p is q, the probability of failure. Yeah, p is the probability of success. So 1 subtracted by p gives you the probability of failure. So again, standard deviation is equal to square root of n p q. Yeah, as simple as that. And the variance of random variable x is, of course, the square root of sigma, or the square root of standard deviation, which is equal to npq. Yeah, so let's take a look at this example. A fair die is rolled 12 times, and random variable x is the number of sixes that could result. Find the mean and standard deviation of the random variable x distribution. Yeah, this is a binomial distribution with n is equal to 12, and the probability of success in this case is 1 over 6. Remember that the random variable is the number of sixes, and for one roll of the dice the probability of getting a 6 is 1 over 6. Yeah, so random variable x is binomially distributed with 12 trials and probability of success 1 over 6. And the formula for the mean, yeah, that is equal to np, number of trial 12, probability of success 1 over 6, and that's equal to 2. And sigma, the standard deviation, is equal to square root of npq, and is equal to square root of 12, number of trials, the probability of success 1 over 6, the probability of failure 5 over 6, which is approximately 1.291. This means when a fair die is rolled 12 times, we expect a 6 to be rolled 2 times with standard deviation 1.291. Right, let's do another example. Here 5% of a batch of batteries are defective. A random sample of 80 batteries is taken with replacement. The question is, find the mean and standard deviation of the number of defective batteries in the sample. Okay, let's write the given information first. This is a binomial sampling situation because there are only 2 outcomes, whether the batteries is defective or not, so that's binomial. Yeah. With n number of trial is equal to 80s, yeah. 80 batteries is taken, so n is equal to 80. The probability of success is equal to 5%, or 1 over 20. Yeah, remember the random variable in this case is the number of batteries which are defective. That is the random variable. Yeah, so if random variable x is the random variable for the number of defective, then random variable x is binomially distributed with 80 trials, and probability of success is equal to 1 over 20. Yeah? This is for each trial. Therefore, the mean, or mu, is equal to NP, which is equal to 80 by 1 over 20, which is equal to 4. And the standard deviation, sigma, is equal to square root of NPQ. Yeah? And again, number of trial, P is the probability of success, and Q is 1 minus P, that is the probability of failure, which is approximately equal to 1.949. Yeah? Therefore, we expect a defective batteries 4 times with standard deviation 1.949 when we do a random sample of 80 batteries is taken with replacement. Yeah. Okay, let's do more examples. Given that random variable x is binomially distributed with 16 trials and 0.8 probability of success, the questions is what is the expected value of random variable x, which is the mean, this is equal to the mean, and variance of random variable x. Okay. Remember the formula for the mean, or expected value of x, is equal to NP, number of trials 16, probability of success is 0.8. Multiply the two to get 12.8. Whereas variance of x is equal to NPQ. Yeah, N being the number of trials, P is the probability of success, yeah, multiplied by Q, which is 1 minus P. We know NP from here, yeah, 12.8, and Q, which is equal to 1 minus P. 1 minus 0.8 is equal to 0.2. So the variance is equal to 2.56. Very straightforward there. Okay, next example. If random variable x is binomially distributed with number of trials equal to 11 and probability of success is equal to 0.25, find the probability of 3 is less than or equal to x and x is less than or equal to 7. Right, here I use calculator. Okay, let me just show you this again. Okay, we go to calculate, menu, probability distribution, and of course here we use binomial CDF, cumulative, yeah, because the given or the required probability of success is given in a range, not an exact value. Here from 3 to 7. Right, number of trials 11, probability of success is 0.25, lower bound in this case is 3 and upper bound is 7. Okay, click OK. There you go. So that's the answer, 0.543. Yeah, the probability of 3 is less than or equal to x is less than or equal to 7. Okay, next one. A binomial experiment has a 0.8 probability of success. Find the probability of having success exactly 17 times in 20 trials. Of course, you can use this binomial probability formula. Okay, knowing n is equal to 20, yeah, because there are 20 trials, the probability of success is equal to 0.8, yeah, and we want to have success exactly 17 times, so x is equal to 17. Yeah. So we input those into this formula. Yeah. So we can write it this way. Yeah. This is n. Yeah. And this is x. This is the probability of success, 0.8 to the power of 17 times 1 minus 0.8. This is the probability of failure, q. Yeah, to the power of 20 minus 17. Yeah, n minus x. Yeah, and that is approximately equal to 0.205. That's if you use the formula. Okay, if you use calculator, it's much easier. Okay, again we go to menu, probability distribution, binomial PDF, because they want number of success exactly 17 times. Okay, there are 20 trials, that's given there, 20 trials. The probability of success, 0.8. And we want to find the exactly 17 times number of success. So click OK. So there you go, that's the answer. Sorry. Yeah, which is 0.205. Yeah, same answer if you do it using the formula. Okay, next one. Suppose you roll a 6-sided dice 15 times and count the number of 5s rolled. Find the probability of rolling at least 3 5s. Round your answer to 3 significant figure. Okay, so we want to get at least 3 5. Yeah, when we roll a 6-sided dice 15 times. So we need to find the probability when the random variable x is equal to 3, yeah, or in this case the random variable is equal to the probability of getting a 5 or rolling a 5, yeah, at least 3 times, 4 times, 5 times, until 15 times. Yeah, it is quite tedious to do, so I don't want to do it using manual calculation. I would prefer using the TI, the calculator. Okay, so again, what you can do, let me just erase this. You go to calculate, menu, probability distribution, right, and in this case we want at least 3 5. Yeah, when we roll a 6-sided dice 15 times, we want at least 3 5. So that means we have to use binomial CDF. Yeah, because the question is not asking for an exact number of success. Right, number of trials is 15. Yeah, because the dice rolled 15 times. Yeah, and the probability of success, well, random variable is, in this case, is obtaining a 5, and the probability of obtaining a 5 is 1 over 6 in one roll. Yeah, in one roll of a dice. Let me just go back. So that is equal to 1 over 6. Lower bound, well, the question wants at least 3 5, so that means 3. Upper bound, well, the die is rolled 15 times, so upper bound has to be 15. Click OK. There you go. That's the answer. Yeah, the probability when random variable x, yeah, is greater than or equal to 3 is equal to 0.468. Yeah. Thank you very much for watching. Take care.